Folks, we're going to recap on the mass on a spring as a simple harmonic oscillator, and then talk about another simple harmonic oscillator that many of you are familiar with. So here's a little schematic of a mass on a spring. And down below, I've drawn this mass in a couple different positions relative to equilibrium, right? So here's equilibrium. Now, when this object is at this location, displaced like this from equilibrium, well, there's a force, F spring, that looks like that, arbitrarily. When this object is displaced this way, by this amount from equilibrium, there is a force back toward equilibrium that is smaller, Fs. All right. Now, we know that these spring forces, many of us do, spring forces are proportional to x. We write them via Hooke's law as kx. And also, we notice that if we're writing this as a vector equation, well, the force is always in the opposite direction of x. And therefore, this is, well, spring forces apply what we call linear restoring forces. And that's, for some people, enough just to say that, okay, that means that if there is a linear restoring force, that means this object is a simple harmonic oscillator. All right? So, you know, do we have a linear restoring force? Check. We do. All right? Can we say, you know, if I say from this that Fs is negative Kx, I can say MA, still keep these as vectors, is negative Kx. All right, and then A is negative K over Mx. Okay, good. Because this now says that, and you know what, I'll write that like this. I'm going to say now that there's acceleration can be written as a function of time, because for this oscillator, position varies as a function of time, right? And now, okay, now we have A is proportional and in the opposite direction of, I'll say delta x. I really should say delta x. All right, so that's another check for simple harmonic motion. Is there a linear restoring force? Yep. And that means that acceleration has to be proportional and in the opposite direction of change in position. Good. Those are two major criteria for an object that is a simple harmonic oscillator. All right. Okay. Now, let's sort of leave that where it is for a sec, and I'm going to jump to a new system of pendulum. Now, for a pendulum, we're going to say this is point mass on a massless string. And we're also, that's kind of one, and two is we're going to say theta max, you know, in the 20-degree range. All right, now notice we have theta here, really a delta theta, because here we're defining this to be equilibrium, theta equals 0. When this object is at equilibrium, right, the mass hangs straight down, and there's 0 angle made between string and vertical. All right, so at a couple different instances, what I want to show you is, you know, we take this instance over here, let's look at, you know what, maybe I'll just draw them where they are. Right now, you know what, I'm going to do it separately. So here's the object. All right, here's mass M at this instant. Now, let's see. Free body diagram says we got a torque, a tension like that, and an mg like this. Yeah? Now, what's the restoring force? All right, well, it might be more appropriate to talk not about the restoring force, but the restoring torque. All right, it's better in this case, I mean, I guess just almost purely because we're talking about angular displacement, to talk about, well, all of our kinematics quantities in their angular or rotational analogs. All right, so we're not so concerned about just the force that restores this thing back to its equilibrium position, but the torque that makes this, or that attempts to restore this object to equilibrium. And that torque, well, there's a torque about this axis that I'll say is, you know, generally up here somewhere. All right, and that torque is provided, well, certainly this tension force exerts no, or creates no torque about that axis as it points right at the axis. But mg has a component that looks like this, that I'll call mg perpendicular, as opposed to mg parallel. And mg perpendicular creates a torque, right? Now, our angle theta is right here, which geometry says is right there. All right. Now, I just do want to show you also that, let me do this, at any other instant, right, this instant, when the object, sorry, is here, if we take that instant, right, and I want to make this thing closer to equilibrium than it was before, which is why I'm saying it's like, you know, like here. Look what happens now. Well, here's the object. It still weighs what it weighs. I actually don't even care about tension because it exerts no torque, but there it is. There's an mg perpendicular now, but guess what? It's no longer this big. All right? Now it looks maybe something, you know, here's the direction of t, and that's parallel, so that's really mg parallel. Looks something like this. And mg perp now looks like that. And notice, it's a lot like this, right? We had, in this case, you know, a relatively large displacement in one direction. We get a relatively large force back in the other direction. Then when we go here, we get a relatively small displacement in the opposite direction, and we get a relatively small force back toward equilibrium. Well, same thing here, right? Relatively large displacement, relatively large restoring force. Relatively small displacement, relatively small restoring force. Now, is it a linear restoring force? That kind of remains to be seen. We'll get there. All right, but I do want to show you how analogous the two cases are. Okay? So if we go back, let me just get rid of this whole set of goodies. What I'm going to do is write a net torque statement. Newton's second law says that net torque is I alpha. All right? Now, the net torque is generally RF perpendicular, and R is the length of the pendulum, right? It's from here to here. R is the distance from the axis of rotation to the point of application of the force. And our force is mg perp. Now, our moment of inertia. Remember, this is a point mass on a massless string. So we don't need to talk about the string as being any kind of rod because it's massless. We don't have to worry about the fact that this object, it's not a ball, so it doesn't rotate as it moves in a path. It just moves in a path. It's a point mass with a moment of inertia mr squared. Mr squared, R is L. Right? R being the radius of this object's circular path. And there's alpha. All right, so notice right off the bat, we can start to simplify. All right, now G perpendicular, really MG perpendicular. Well, now it's really just G perpendicular. Right, here's MG perpendicular, opposite that angle. So that would have been MG sine theta. I'm just going to keep the G. There's our sine theta is L alpha. All right, now, here's the deal with criteria number 2. Angles being less than 20-ish. All right, let me take a little sidebar here. Angles being less than 20-ish allow you to say the following. Here's a triangle. Small angle theta. Here's adjacent side. Here's opposite side. Here's hypotenuse side. Well, for small angles, and quite literally, people usually say it's 20-ish or less, it happens that A and H are about the same size. I mean, look at them, there they are. All right? Well, O is O, so that means that O over A is approximately the same as O over H, because A and H are approximately the same thing. Well, O over A is, by definition, tangent of theta. And O over H is, by definition, sine of theta. So it says for small angles, those are approximately the same thing. Well, that's pretty true. I mean, you look at the sine of 12 degrees. Sine of 12 degrees. Sine 12 degrees. 0.21. Tangent. 12 degrees. Let's say tangent. Come on. 0.21. Oh, okay. That's good. Now, check this out. 12 degrees. Well, in 360 degrees, there are 2 pi radians. Notice, right, when we talk about, we want to talk about radians and radians per second squared. Well, guess what? 12 degrees, 12 times 2 pi divided by 368 is, 12 degrees is 0.21 radians. This small angle approximation allows us to say, if angles are, relatively small, why did I pick 12? Because it's, less than 20. Then these are basically just theta. So when I see sine theta, I can just say theta. So this is, oh, darn, you know what I didn't do, which I always never do, is I didn't say this. I didn't say that, well, maybe it works to do now. First of all, I'm just going to say sine theta is approximately theta. And L alpha. What I have not accounted for is the fact that we're saying that there's an angular displacement, theta, that way. Well, this mg force creates an angular acceleration back toward equilibrium. I'll throw that negative in there. That's the restoring part. And it probably belongs up here, that the torque is a restoring torque. All right, and you'll notice we're getting to a good place where, look, before I strove to write acceleration in terms of position, right? Well, I can do that here. It's just angular acceleration. And look, I can write angular acceleration is, let's see, negative g over L times theta. All right? So look, what I get is something very analogous to this. Acceleration is proportional and in the opposite direction of position. Well, here, acceleration is proportional, right? Direct relationship. No squareds or square roots or inverses, just theta, and in the opposite direction. So yeah, we have a good justification for the fact that that the pendulum is a simple harmonic oscillator. And because, well, it's an oscillator, it means that really theta varies as a function of time, and therefore alpha varies as a function of time. And this allows us to say, where'd that come from? This allows us to say that, yeah, acceleration is proportional to and in up direction of displacement. Whoa, displacement. Thus it is demonstrated this is a simple harmonic oscillator. Okay? Now, I want to take this copy. I want to go here. I want to say bye-bye. Paste. Okay, I want to go here. Grab this, no this, no all of this. Copy. Go. Paste. Okay. Please note the similarities. So here's mass on spring. Here's pendulum. Now, for an object that is a simple harmonic oscillator, the position varies as a function of time and can only vary as a function of time in one way. There is only one function that will allow for the, well, follow me here, the rate of change of the rate of change, right? Well, the rate of change of this is velocity, and acceleration is the rate of change of velocity. So acceleration is the rate of change of the rate of change of position. There's only one function whose rate of change looks just like the original position. And so we said that, remember this? We said that if x, say, looks like that as a function of time, then a is going to look like this as a function of time. There's only one function that behaves that way, and so what we said is, you know, the position function is x max, I'll say cosine omega t. And then a is a max cosine omega t, but it's a negative cosine function, right? Here's a max and here's x max. And remember, we want a max to be measured in meters per second squared. So I can make that happen if I take meters and per second and square them. So I can turn this into negative omega squared x max cos omega t. And then if this goes in there, and this goes in here, well, check it out. This is actually just x as a function of time. So this says that a as a function of time is negative omega squared x as a function of time, right? Here's the negative omega squared. A as a function of time is negative omega squared x as a function of time. Well, a as a function of time is also this. So that says that negative k over m x as a function of time is negative omega squared x as a function of time. And therefore, well, bye-bye, bye-bye. Ah, darn you. Bye-bye. We get for a mass on a spring, boop, that angular frequency is square root of k over m. All right? Well, these same graphs can be used to describe the position and linear acceleration of a mass on a spring, or they could be used to talk about the angular position and the angular acceleration of a pendulum. Right? So theta as a function of time, we can write as theta max cosine omega t. And alpha as a function of time is alpha max cosine omega t. But it's a negative cosine function. And then we can say, well, alpha as a function of t. Let's see, alpha we want is radians per second squared. Well, here's the radians, and we can get per seconds and square them. So we get our negative. If I went omega squared theta max cosine omega t, well, look, this part is just theta as a function of time. So this says that alpha as a function of time is negative omega squared theta as a function of time. But look, alpha as a function of time is also this. So that means we can write negative g over L theta as a function of time is negative omega squared theta as a function of time. And goodbye, goodbye. For a pendulum, hello, hello, angular frequency can be written as the square root of g over L. All right? So these two systems, while they certainly look different, they're very analogous. And while they're, you know, made of different parts, those parts can kind of perform the same function, right? I mean, you know, the thing about a pendulum is it requires a gravitational field in order to oscillate. A mass on a spring doesn't, right? A mass on a spring requires a spring and a mass, right? A pendulum requires a pendulum of length L and a gravitational field G to operate it. A gravitational field G that will provide the force on the mass. For a mass in a spring, the spring provides the force. All right, but these two expressions are, you know, they're definitely analogous. They have the same form, right? And they come from very similar analyses. Okay, so you know, really for simple harmonic oscillators, you got to be able to talk about, you know, what is it that makes an object, or a system, I should say, a simple harmonic oscillator? Well, there's a linear restoring force, and acceleration is proportional in the opposite direction of displacement. Same thing here, except there's a linear restoring torque. All right, we didn't really write it explicitly. Maybe I should have up here. I'll just say this is R. I mean, we know it now. Mg sine theta is I alpha. Well, this is the torque. And remember, sine theta is just theta, or is equivalent, or is approximately equal to theta. So that is what I would call a linear restoring torque. All right? So we meet that criteria, and then we meet the criteria here that says acceleration is proportional to and in the opposite direction of displacement. So yeah, this thing meets our criteria for being a simple harmonic oscillator. All right, and then we can get into the you know, time dependence of each of these functions, and really get to a derivation of why the angular frequencies are what they are. Okay? Okay, folks. See you soon.